Good morning. Welcome back to our two-part series the on significant changes from ASCE 716 to 22, with emphasis on seismic design and to an extent design for wind forces. Last week we spent a lot of time on chapter 11, which is the first seismic chapter, which deals with seismic design parameters related to seismic ground motion that we use in design. There are big changes in that area that absolutely needed to be discussed in detail. Then we started on chapter 12, which is design of building structures. The major topics that we have already discussed are new structural systems in table 12.2-1, the ductile coupled concrete shear wall system, the composite steel plate concrete coupled shear wall system, and the CLT shear walls. We discussed changes in two-stage analysis procedure. We discussed changes in the structural irregularity provisions of ASCE 7. So we will now continue from where we left off. The next change, I don't think this is a particularly big one, in section 12341, that deals with redundancy factor rho. We have a list of situations where rho can be taken equal to 1. And one item has been added in that list. In diaphragm design section 12.10, we had until ASCE 716 section 1210.1, the conventional diaphragm design force level, if I may call it that, the diaphragm design force level that we have been using since the UBC days. Then there is section 1210.3, which is alternative seismic design procedure, which is mandated for precast concrete diaphragms design categories C and above. Now in ASCE 722, we have section 12.10.4 giving you a yet different force level, diaphragm design force level for rigid wall flexible diaphragm buildings, the big box buildings that we see all over the place, masonry walls typically laterally supported by flexible diaphragms. For the diaphragms in those buildings, we have design force level given in section 12.10.4. And what you are seeing here is that if we design for the diaphragm design forces given in section 12.10.4, then redundancy factor rho is equal to 1. The next item was there before. I discussed with you the last time that we do not use the terminology extreme torsional irregularity anymore. It is torsional irregularity, which is triggered by the torsional irregularity ratio TIR exceeding 1.2. There is a table that tells you the ASCE 7 provisions that are triggered when the torsional irregularity ratio goes beyond 1.2, then when it goes beyond 1.4, and then when it goes beyond 1.6. Anyway, what this is saying, and it may be better to read. So for a structure assigned to design category D, E, or F, having a type 1 horizontal irregularity, torsional irregularity, but with the torsional irregularity ratio larger than 1.4, that would have been extreme torsional irregularity in ASCE 716 language. Okay. So if we have extreme torsional irregularity in old language in both orthogonal directions in any given level, rho shall be equal to 1.3 for the entire structure in both orthogonal directions. So if you have an extreme torsional irregularity in both orthogonal directions at any given level, rho shall equal 1.3 for the entire structure in both orthogonal directions. I said it is not really new because we had this provision in ASCE 716, except that we said if you have extreme torsional irregularity, now we say if you have irregularity type 1 with torsional irregularity ratio larger than 1.4. So only the terminology has changed, not the provision itself. Okay, if we have a horizontal cantilever, design category D, E, or F, structural member shall be designed for a supplemental basic load combination consisting of a minimum net upward force of 0.2 times the dead load. This we have been doing for a long time. Okay, if you have a horizontal cantilever, you design it for a net upward force of 0.2 times the dead load. So that is nothing new. What has been added is the 0.2 times dead load has always been for strength design, and now we are adding the net upward force shall be 0.14 times the dead load if we are using allowable stress design. 0.14 being simply the 0.2 multiplied by 0.7. Okay, so the three items we discussed so far are definitely not big changes. Direction of loading. This is where we consider the fact that earthquakes can come from any old direction, and we have to consider orthogonality effects in many cases. Okay, so the section 12.5 on this topic, direction of loading, is rewritten. However, only the requirements for seismic design categories D through F have substantive changes. Okay, so if it is lower seismic design categories, whatever we have been doing has not changed, like one direction at a time for low seismic design categories. So we will look at the changes seismic design categories D through F. I said mostly new. It is not, definitely not all new. I'll point out what was there, what has been added. Okay. So for a structure assigned to design category D, E, or F, so up to design category C, the requirements have not changed. The independent directional procedure shall be permitted. Independent directional procedure means you design your structure one direction at a time. Okay. No orthogonal effects to be considered. So even for a structure assigned to design category D, E, or F, the one direction of a time shall be permitted unless one or more of the conditions exist. So when are we not going to permit one direction at a time? If the structure has torsional irregularity, horizontal type 1, if the structure has type 5 horizontal irregularity, that is non-parallel seismic force resisting systems. And then importantly, so those A and B are for entire structures. Starting from C, we are talking about structural elements, element in a structure. The element has to be designed considering orthogonal effects. So which elements have to be designed considering orthogonal effects? A column that forms part of two or more intersecting seismic force resisting systems. So if you have moment resisting frames in both directions, any column at the intersection of the frames is part of intersecting seismic force resisting systems. So any of those columns that are subject to seismically induced axial force exceeding 20% of the axial design strength of the column. This is not new. This we have had for a long time. I cannot tell you how far it goes back. So if a column is part of intersecting seismic force resisting system, and the seismically induced axial force in the column, not gravity, is more than 20% of the axial design strength of the column has to be designed considering orthogonal effects. Okay. Now, up to what I read, absolutely nothing is new from ASCE 716. The new stuff comes here. Okay. So this we didn't have up until now. Just like a column, ASCE 722 is now saying you shall design considering orthogonal effects a concrete shear wall that has connected intersecting wall planes, and so the shear, it's a concrete shear wall. It has intersecting wall planes, so it can be a flanged wall or something like that, and axial demand exceeding 20% of the axial design strength at any location in the wall due to seismic forces acting along either principal plane axis. So we are saying pretty much the same thing as in the case of columns, okay? So seismically induced axial force exceeding 20% of the axial design strength. So the requirement we had concerning columns common to intersecting seismic force resisting systems, we now have similar requirements for concrete shear walls that are part of what's the language, has connected intersecting wall planes, a masonry shear wall that has connected intersecting wall planes, a wood or coal form light or coal form steel light frame shear wall that has connected intersecting wall panels. Okay, all of those shall be subject to design considering orthogonal effects if the seismically induced axial force anywhere in the shear wall exceeds 20% of the axial strength. Okay, so design axial strength. I think if you read, you will see that it just mirrors the column requirements. Very importantly, cantilever column systems are now in the list. Okay, so cantilever column systems have to be designed considering orthogonal effects. This is new in ASCE 722. Now, where items A and B do not apply, item A, remember, if a structure has torsional irregularity, item B is if a structure has non-parallel seismic force resisting systems. Where items A and B do not apply, if we don't have that situation, either torsional irregularity or non-parallel seismic force resisting systems, the independent directional procedure is permitted to be used for components of the seismic force resisting system not listed in items C through G. This is very, very important, okay? So you have a structure that is not torsionally irregular, that does not have non-parallel seismic force resisting system. There may be 36 columns. Out of those 36 columns, maybe 4 of them meet the requirements that we told you about. The column is part of intersecting seismic force resisting systems, and the seismically induced axial force in the column is more than 20% of the design axial strength. So if only 4 columns meet those requirements, then only 4 of the columns have to be considered, have to be designed considering orthogonal effects. The other 32 columns in the building can be designed one direction at a time, no orthogonal effect considered. Okay, so that is extremely important to understand. Then I do not believe the remaining language was in ASCE 716. Foundation elements and connections that support elements of structures with any of the preceding conditions C through G. So these columns and shear walls that we talked about, foundation elements and connections that support these columns and shear walls shall be designed using the orthogonal direction combination procedure. So it is not only those columns and shear walls, but also their foundations that have to be designed using orthogonal effects. In addition, foundations and connections supporting lateral force resisting system elements that are not coplanar. So you understand coplanar. So we have a shear wall that changed. So that is not, that changes. It's an east to west to east shear wall. Halfway along, it takes a 30-degree turn. Okay, so if that is what your shear wall has done, the foundation has to be designed considering orthogonal effects. Okay, so in addition, foundations and connections supporting lateral force resisting system elements that are not coplanar shall be designed using orthogonal effects. And now a huge change. So we have had how should I preface it? We have always been given to understand that dynamic analysis, starting from modal response spectrum analysis, gives us more accurate results than equivalent lateral force procedure. So up until ASCE 716, we were allowed to use equivalent lateral force procedure only under certain restrictions. Not all buildings could be designed using the equivalent lateral force procedure. This table told us when equivalent lateral force procedure was permitted and when it was not permitted. Okay. So this table 12.6-1 has been deleted completely from ASCE 722 because the equivalent lateral force procedure is now always allowed. There have been studies showing that the collapse probability of a structure does not change whether you design it using equivalent lateral force procedure or modal response spectrum analysis or something more sophisticated. So instead of the table, we now have this new requirement, and this is extremely important, obviously. The structural analysis required by Chapter 12 shall be completed in accordance with the requirements of equivalent lateral force procedure, modal response spectrum analysis, linear response history analysis, or this is the most interesting part, an analysis procedure approved by the authority having jurisdiction. Any analysis procedure that is approved by the authority having jurisdiction. So you have the power to approve an analysis procedure that can be used in the analysis of a structure, in the seismic design of a structure. Okay, so there are no restrictions on the equivalent lateral force procedure. Nonlinear response history analysis obviously has always been permitted to be used, and that continues. So this change uh, how should I say? How should I say it? It goes against things that most of us have believed for much of our professional lives. And when I have brought this up abroad in countries outside of the US, there is almost consternation. How can it be that we enforce uh, moral response spectrum analysis in some situations? Uh, anyway, all I can say is that ELF is now allowed. That does not mean that uh, moral response spectrum analysis does not have its virtues. It definitely gives you a better distribution of the lateral forces along the height of the structure. So this permission to use equivalent lateral force procedure should not be taken as a directive not to use the more sophisticated procedures. Okay, but this is a big change. I absolutely have to emphasize that. Okay. Uh, Effective seismic weight, it includes a number of items. Item number 4 used to say where the flat plate roof load exceeds 30 pounds per square foot, 20% of the uniform design snow load shall be included in the effective seismic weight. The 30 pounds per square foot has changed to 45 pounds per square foot because snow is now at strength level, as I kept on saying a number of times last week. And because of the same reason, the 20% is now 50%. Okay, so because snow is at strength level, these changes were necessary. Also, this is a new item that is included in the effective seismic weight. Weight of fluids and bulk material expected to be present during normal use. So weight of fluids and bulk material expected to be present, expected to be in the structure during normal use. Okay. So this has been added, but then an exception also has been added. The weights of fluids included as effective seismic weight are permitted to be reduced as justified by a rational fluid structure interaction analysis. I do not know anything about that kind of analysis, but anyway, you having said that weight of fluids and bulk material shall be included, there is this exception that you can reduce the weight of fluids. Okay, we are kind of back to a topic I think I spent quite a bit of time on last week. ASCE 722 has introduced multi-period response spectra, section 11.4.5.1, but the two-period spectrum is definitely still there. Because of the language used in ASCE 722, many people were under the impression that in the equivalent lateral force procedure, where a multi-period spectrum is available, which is everywhere in the United States, all 50 states, you have to use modal response spectrum analysis that not modalist, you have to use the multi-period spectrum, not the continued use of the two-period spectrum in the equivalent lateral force procedure shall not be allowed. Now that I emphatically point out is not the case. The use of the two-period spectrum, continued use of the two-period spectrum in the equivalent lateral force procedure, which is section 12.8, is still fully allowed. Okay, so this is what this section is about. 12.811 calculation of seismic. So where the design spectral acceleration parameter S sub A determined in accordance with 11451, which is multi-period design spectrum, or chapter 21, which is site-specific response spectrum. So where the design spectral acceleration determined in accordance with either the multi-period spectrum or site-specific spectrum is available, you can use either method 1 or method 2. Method 2 is the 2-period spectrum, okay, whatever we had in ASCE 716. So either method 1 or method 2 is permitted to determine the seismic response coefficient C sub S. Okay, cannot be any clearer. So you have multi-period spectrum. You are going to use equivalent lateral force procedure. You can use either method 1 or method 2. Method 1 is use of the multi-period spectrum, and you will see it on the next slide. Method 2 is kind of going back to the 2-period spectrum. Both are allowed. Where exception 2 of section 11.4.5 applies, meaning you do not have multi-period spectrum available to you. You are at a location outside of the United States. You do not have the information. Then method 1, which is use of the multi-period spectrum, it says shall not be used. It basically cannot be used. If you don't have a multi-period spectrum, how are you going to design using multi-period spectrum? So if you have a multi-period spectrum, you can use method 1 or method 2. If you don't have a multi-period spectrum, you cannot use method 1. The lower bound for the seismic response coefficient, we have various lower bounds on the design base shear. The seismic design coefficient is simply the design base shear divided by the effective seismic weight. So the lower bound on the seismic response coefficient provided in item 3 shall be applicable to both methods 1 and 2. So all the lower bounds apply, whichever method you are going to use. So method 1 is direct use of the multi-period spectrum. So the seismic response coefficient C sub S, again, it is V over W, is simply the spectral response acceleration from the multi-period spectrum divided by R multiplied by I, the importance factor. It is divided by R because the multi-period spectrum is reflective of elastic response. We have been doing that in the equivalent lateral force procedure for a long time. We reduce by R and we multiply by I sub E. We increase the seismic design force for higher occupancy structures. The idea being that non-structural components will be spared damage and the facility will go on functioning during and following an earthquake. Okay. So it is very simple. You go to your multi-period spectrum. You have the period of the structure. You pick the corresponding spectral acceleration. That divided by R multiplied by I sub E is your C sub S, the seismic response coefficient. It's base shear divided by W. Okay. So the last two lines is fairly important. So when you use this equation that you see on the screen, C sub S is equal to S sub A divided by R over I sub E. If the period T, that the period of our structure is less than the period at which S sub A is maximum, the maximum value of S sub A shall be used. I probably should have added a figure. So we are talking about the very short period part of the spectrum. Okay, so you start with 0 period. You climb to the period at which the spectrum peaks. You have the period at which S sub A has its maximum value. Okay, if your period is less than the period at which S sub A gets to its maximum value, then you will take your spectral acceleration equal to the maximum spectral acceleration. Okay, you will not go, if you're on the ascending branch, short period part of the spectrum, where you are going from 0 period to the period at which we have S sub A maximum. Okay, you will not use any spectral acceleration value lower than the maximum. Okay, so please read these last two lines. I think the meaning is quite clear, but this is a pretty important provision for short period structures. Okay, method 2 is the same as what we had up to ASCE 716. It continues. In ASCE 722, it tells you exactly the same thing as it did in ASCE 716. But I pointed out emphatically last week, that the 2-point spectrum of ASCE 722 is not the same as the 2-period spectrum of ASCE 716. The spectrum has changed, and I hope you retain that information. Okay, so okay, then this is kind of a remnant of the past. So in the UBC days, we used to say that you don't have to design a structure for a peak ground acceleration more than 40% of G. That has evolved over the years to S sub ds doesn't have to be taken more than something. Okay, so let's read this now. The values of C sub S, the V over W, and E sub B, that's vertical earthquake effect. Remember, 0.2 S sub ds times D. So C sub S depends on S sub ds. E sub B depends on S sub ds. The values of C sub S and E sub B are permitted to be calculated using a value of S sub ds equal to 1. So that is the ceiling. Used to be 40% G on the peak ground acceleration. Now it is 1.0 on S sub ds, which are kind of equivalent. So it used to be peak ground acceleration not more than 40% of G, period. But then we started adding requirements. So now S sub ds equal to 1.0, but not less than 70% of the value of S sub ds, as defined in section 11.4. So you will not go below 70% of the value that you would have used if there were no ceiling. So that 70% was added some time ago. We now have a new requirement for you to cap S sub ds at 1.0. The response modification factor R is 3 or greater. Okay, so very low R value systems, you will not be allowed to use this cap of 1.0 on S sub ds. This is a new restriction. So the R is 3 or greater for the structure for which you are trying to find C sub S or E sub B by using the cap of 1.0 on S sub ds. The next one, this is definitely not unimportant. So this is torsional, accidental torsion. Okay. Delta maximum divided by 1.2 delta average squared. Okay, you are doubtless familiar with it, so I wouldn't, and we have discussed delta maximum, delta average the last time. For the purpose of computing this delta maximum and delta average, it shall be permitted to assume the diaphragm is rigid. This is newly, how should I say, this explicit statement is new in ASCE 722. Many of us probably were doing it anyway, but now it is officially sanctioned, and obviously it helps to have this explicit statement. Okay, we are now coming to displacement and drift determination, important topic. And here, ASCE 722 has made pretty significant changes that do not quite stand out. That's the best way I can put it. Okay, so until you read very closely or somebody points it out, you may not even pay attention to the fact that the requirements are now in some ways substantially different from before. So, excuse me. So displacement and drift determination. So the first change is the elastic analysis of the seismic force resisting system for computing displacement and drift. Obviously, the displacement and drift will come from analysis of the structure under what I typically call code prescribed seismic forces. Okay, so and this is the analysis that we are talking about, the elastic analysis of the seismic force resisting system for computing displacement and drift shall be made using the prescribed seismic design forces of 12.8. So this is the equivalent lateral force procedure seismic design forces. Up to that is no different from before. But now we are adding, when you use the code prescribed seismic forces, the load factor on horizontal earthquake effect is 1.0. That's what we have practiced. The code didn't say anything, but that was understood. But then in the presence of, so you are doing lateral analysis for the purpose of computing drift, you have to have sitting on your structure a certain amount of gravity load in the presence of expected gravity loads. Expected gravity loads shall be taken as no less than 1.0 times dead load plus 0.5 times live load. So when you do your elastic analysis for the purpose of computing drift, you don't do your analysis only under the prescribed seismic forces. You have to have sitting on the structure expected gravity loads 0.5 dead plus, 1.0 dead plus 0.5 live. This live load is reduced live load, L. The notation tells you that. This L shall be taken as 80% of the unreduced live load for live loads that exceed 100 pounds per square foot, and the reduced live load shall be taken equal to 40% of the unreduced live load for all other live loads, okay? All live loads that don't exceed 100 pounds per square foot. So the change is that the lateral analysis for the purpose of determining drift and displacement must be carried out with a certain amount of gravity load sitting on your structure. That expected gravity load is 1.0 dead plus 0.5 live, and the reduced live load that we are talking about, 0.5 times reduced live load, that is prescribed. Okay, that is 80% of the unreduced live load if the live load is heavy, and 40% of the unreduced live load if the live load is not heavy. Okay. Design earthquake displacement. Most of you would remember up until ASCE 716, in this section, we used delta sub XE, elastically computed displacement at floor level X. We don't talk about delta sub XE anymore. It is delta sub E, elastically computed displacement. Okay. Where is this displacement? Let's read the design earthquake displacement. The design earthquake displacement has a notation now, delta sub capital D, capital E. Okay, so delta sub DE, this is new notation in ASCE 722, shall be determined. We are not talking about floor level anymore, at the location of an element or component. Okay, so delta sub DE is the design displacement at the location of an element or a component. The element means structural element, component means non-structural component. This is the terminology ASCE 7 has been using for quite a while. So the design earthquake displacement shall be determined at the location of an element or component by using the equation that you see there. Okay, so delta sub DE is delta sub E. We used to use delta sub XE. Okay, it is now delta sub E. We multiply by C sub D as before. We divide by I sub E to take importance factor out of the picture. The load under which you are computing displacement is amplified by the importance factor I. We divide by I to nullify that amplification, because the drip limits are dependent on the importance of the structure. A hospital has half the drip limit of an office building on the same site. And we don't want to penalize a hospital twice, once by instituting a tighter drip limit, a second time by calculating larger drifts under earthquake forces that are augmented by an importance factor. So this is why we have always taken the importance factor out. Okay. So the delta sub DE, the design earthquake displacement at the location of our component or element, is delta sub E multiplied by C sub D as before, divided by I sub E. And then there is an added term which we didn't have in ASCE 716. Now, first of all, what is delta sub E? Elastic displacement computed under design earthquake forces, including the effects of accidental torsion and torsional amplification as applicable. Okay, so delta sub XC used to be at floor level X. Delta sub E is at the location of the element or component. That is something you should note. Now the added term delta sub DI is displacement due to diaphragm deformation corresponding to the design earthquake. Displacement due to diaphragm deformation corresponding to the design earthquake. Now, in addition to design earthquake displacement, we now have in ASCE 722 maximum considered earthquake displacement. Okay, and that is, so maximum considered earthquake is 1.5 times the design earthquake. So you would expect delta sub MCE to be, 1.5 times what you see here. Okay, that would be what is expected. Now, the 1.5 is there as you would expect, but then instead of C sub D, ASCE 722 has decided to use R. So in other words, for calculation of delta sub MCE, C sub D has been taken equal to R. This is in order to be more conservative. this maximum considered earthquake displacement is used in, so if you have a bridge between two buildings or two towers, the the when the two towers go displace away from each other, the bridge still has to be supported, right? So in this case, we need to calculate the lateral displacement as conservatively as is reasonable. Okay, so we multiply the design earthquake displacement by 1.5, but then the displacement amplification factor C sub D is taken equal to R when we go from the delta sub E to delta sub MCE. Okay. Okay, now the first line. Okay, let me read. So the design story drift. So we are talking about displacement so far. Now it is drift. The design story drift shall be computed as the difference of the design earthquake displacements as determined in accordance with 1286 at the centers of mass at the top and bottom of the story under consideration. Okay, so if we want to consider or calculate inter-story drift for a particular story, we will take the displacement at the center of mass of the floor level above. We will deduct from that the design earthquake displacement at the center of mass of the floor level below. Okay, this is how we have always done it. Where centers of mass do not align vertically, it is permitted to compute the deflection at the bottom of the story based on the vertical projection of the center of mass at the top of the story. This is exact language in ASCE 716. So this is why I said the section is new. However, much of it was in ASCE 716, section 1286. So nothing really has changed as far as this slide is concerned, except, we didn't have delta sub DE notation in ASCE 716. Same thing is pretty much true of what is said on the next slide, except for the very first line, which is extremely important. So the diaphragm deformation that we have now added may be neglected in determining the design story drift. This is extremely, extremely important. Okay, so we have added that term, but when it comes to drift determination, the added term can just go. It can be disregarded. And then diaphragm rotation shall be considered as follows. This is ASCE 716 language. For structures assigned to design category D through F, if you have torsional irregularity, the design story drift delta shall be computed as the largest difference of the design earthquake displacements of vertically aligned points at the top and bottom of the story under consideration along any of the edges of the structure. We had this exact language. So the idea is that you would go around the perimeter and figure out where you have the largest difference between the displacement at the top of the story and the displacement at the bottom of the story that are vertically aligned. Now, in reality, we don't go around the perimeter. We have pretty much an idea where to look for the maximum difference. But anyway, no change here from ASCE 716 to 22. Diaphragms, cords, and collectors. Whatever I have on this slide is identical to ASCE 716, no change. Okay, so diaphragm, cords, and collectors shall be designed in accordance with 1210.1. This is the conventional seismic design force level. The diaphragm itself is designed by 1210.1. The cords and collectors are designed by section 1210.2. Okay. The exception said there are a couple of exceptions. So precast concrete diaphragms, this came up already, including cords and collectors in structures assigned to design categories C, D, E, and F shall be designed in accordance with 1210.3. The alternative diaphragm design force level that we added in ASCE 716. Okay, nothing here is new. This is ASCE 716 language. Now, what is new is that in the second exception, we have added certain things, and then the third exception has been added. The second exception says, so having said that precast diaphragms design categories C and above shall be designed using the alternative design force level, we are now saying precast diaphragms design category B, cast in place concrete diaphragms, cast in place concrete equivalent precast diaphragms. This is something defined in chapter 14 of ASCE 722. We will move it to let me not go there. So cast in place concrete equivalent precast diaphragms. Think of these as the topping on precast, acting as the diaphragm. Okay. So precast diaphragms design category B, cast in place concrete diaphragms, cast in place concrete equivalent precast diaphragms, wood sheathed diaphragms supported by wood diaphragm framing, bare steel deck diaphragms, and concrete filled steel deck diaphragms are permitted to be designed by. They don't have to be designed by, but they are permitted to be designed by section 12.10.3, the alternative design force level. Okay. So in this list of diaphragms that are permitted to be designed using the alternative design force level, the additions are in ASCE 722, cast in place concrete equivalent precast diaphragms, bare steel deck diaphragms, and concrete filled steel deck diaphragms. Those are additions. And then a brand new exception, diaphragms, cords, and collectors in one-story structures that conform to the limitations of 1210.4 are permitted to be designed in accordance with 1210.4. Okay, so the big box buildings that I was talking about, the rigid wall flexible diaphragm buildings that meet the criteria that are included in ASCE 722 can be designed by section 1210.4. We don't have to use 1210.1 or 1210.3. These are the buildings that I was talking about. A rigid wall, you can see, and flexible diaphragm, you can also see. So there is a FEMA 1026 report. FEMA 1026 recommendations for seismic design of the rigid wall flexible diaphragm building type included. Why are these buildings different? So the recommendations included a recognition that the diaphragms often yield and dominate the building behavior, while the walls typically remain mostly in the elastic range for in-plane loading. We have a lot of walls typically in plane for when those walls act as shear walls, they are quite rigid, but the diaphragms are flexible. Okay, and the diaphragms dominate the dynamics of the building. Recognizing the item 2, recognizing the distinct period of both the shear wall system and the diaphragm, and using a two-stage equivalent lateral force analysis to capture this distinct behavior. This is rather complicated. You have to go into it. I didn't include a discussion of this, but they are treating the diaphragm and the walls like tower on podium, okay, for design purposes. And then proposing the creation of a zone of reduced nailing away from the diaphragm perimeter where distributed yielding can occur without jeopardizing the diaphragm connection to the vertical elements. So if we have distributed yielding in the middle of the diaphragm, that shouldn't harm anybody. And so the recommendation is to allow reduced nailing in that middle zone. So there are two changes in the section 12.10.4, not so one change addresses the first and the third bullet, the recognition that the diaphragm dominates the behavior of the building, and the third is the creation of a zone of reduced nailing away from the diaphragm perimeter. Okay, those two are one change, and recognizing the distinct periods of the diaphragm and the wall is another change. So one change addresses the first and third bullet points, while the second change addresses the second, that two-stage analysis. Use of the alternative diaphragm design forces of 12.10.4 is permitted for any structure meeting the limitations in 12.10.4.1. We will look at those limitations. And irrespective of whether, so you can use the 12.10.4 procedure or force level without doing the two-stage analysis, okay, irrespective of whether the two-stage analysis procedure is used. However, the two-stage analysis procedure cannot be used if you are not designing by section 12.10.4. Where permitted by section 12.10, the subject of the and subject to the limitations of 12.10.4.1. So there are limitations that you have to satisfy in order to use the design force level of section 12.10.4. What are the limitations? It's a long list. All portions of the diaphragm shall be designed using the provisions of this section in both orthogonal directions. Okay, so if you decide to use 12.10.4, you have to design it for all portions of the diaphragm in both directions. You cannot pick and choose. The diaphragm shall consist of either a wood structural panel diaphragm designed by special design provisions and fastened to wood framing members or wood nailers with sheathing nailing in accordance with also the special design provisions, section 4.2. The shear capacity tables in table 4.2. The nailing has to be in accordance with that table. So wood diaphragms satisfying those descriptions, or a bare or untopped steel deck diaphragm that meets AISI S400 and S310. Topping of concrete or similar materials that affect diaphragm strength and stiffness shall not be placed on the wood structural panel or bare steel deck diaphragm, so they have to be untopped. The diaphragm shall not contain horizontal structural irregularities except re-entrant corner irregularity is permitted. The diaphragm shall be rectangular in shape or shall be divisible into rectangular segments for purpose of seismic design with vertical elements, and you can read the rest. The vertical elements of the seismic force resisting system shall be limited to one or more of the following: concrete shear walls, precast shear walls, masonry shear walls, steel eccentrically braced frames, steel and concrete composite brace frames, or steel and concrete composite shear walls. So these have to be rigid seismic force resisting systems, no frames. The vertical elements of the seismic force resisting system shall be designed in accordance with 12.8, the equivalent lateral force procedure, except that they shall be permitted to be designed using the two-stage analysis procedure. Okay. So that is the new section 12.10.4. Wall anchorage forces. I don't know how time is running. We started at what time?
9.
9:30, right?
9:30.
9:30 our time. So it's 1 hour. I think let us break for we have talked for an hour. I think this is a good time to. Okay, let's take a 5-minute break right here. Okay, Maria tells me 5 minutes are over and there are still no questions, so I will proceed. This is anchorage of walls. So we have wall laterally supported by diaphragm. We are talking about the connection between the wall and the diaphragm, the anchors that connect the walls to the diaphragm. These anchors are crucial, and the failure of these anchors have caused major problems and failures in past earthquakes, as you all know. And this anchor design force kept on changing. Anyway, now we have stability. The anchor design force in ASCE 722, no different from that in ASCE 716, is what you see on the screen. 40% S sub ds, that's supposed to be close to the peak ground acceleration, multiplied by K sub A that I will explain to you, multiplied by the importance factor I sub E that we are familiar with, multiplied by the W sub P, which is weight of the wall tributary to the anchor. Weight of the wall tributary to the anchor. Okay, so that equation is unchanged. The changes are underlined. So F sub P shall not be taken as less than the larger of 0.2 K sub A, I sub E, W sub P, and what is new is 5 pounds per square foot. So previously the minimum was 0.2 K sub A, I sub E, W sub P. Now it is the larger of the old value and 5 pounds per square foot, okay, times the area of the wall tributary to the anchor. So this minimum of 5 pounds per square foot is what is new. And that comes up in another place. I think it's unnecessary to the same thing. The, the minimum now not less than 5 pounds per square foot. Now, what is this K sub A? It's amplification factor for diaphragm flexibility. So L sub F is the span. I will show you. Let me show you that. So L sub F is the span, but which span? Is it the up and down span or the left to right span? So what you are seeing in the picture, I have no way of pointing. I don't know if you see my cursor. This is the wall. This is the diaphragm providing lateral support. These are the anchors that we are talking about. Okay. So L sub F is the span from this this frame or wall provides lateral support to the or the flexible diaphragm provides lateral support to this frame or wall in the other direction. So anyway, the picture is clear enough. L sub F is this span, the span shown in the picture, not the perpendicular span. And K sub A depends on the L sub F. If L sub F is 100, then you get a value of 2. We do not go beyond 2. If L sub F is 30 feet, then we get a value of 1.3 for K sub A. Okay. So nothing has changed except the 5 pounds per square foot minimum, which is new in ASCE 722. Okay, chapter 13, non-structural components. Very big changes this time around. I did not think that in two 2-hour seminars I could do much about the non-structural components. So I have a few things that I want to mention to you, and then we will go on. Okay, so uh, the 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 changes this time are very major indeed. I absolutely want you to understand that. Okay. A large multi-year study was undertaken to gain a holistic understanding of the response of non-structural components to earthquakes. A range of parameters were thoroughly investigated for their effect on the seismic performance of different types of non-structural components. The goal was to overhaul the code provisions almost from the ground up in order to minimize costly and disruptive non-structural damage. The investigation was ATC 120. Some of you may have heard about it. Anyway, it resulted in two publications. The left-hand one is background and recommendations for future work, but the right hand is recommendations for improved seismic performance of non-structural components. And the changes in chapter 13 have been based on those recommendations. So in this ATC 120 study, some of the parameters investigated were found to have no significant influence. That's an important finding. The effects of some other parameters were found to be too complex, requiring more research before they could be added to the code. The rest were incorporated in an updated set of provisions. So there are updates, significant updates, many of which are based on the ATC 120 study. So major changes in this chapter: changes in the design provisions for heavy non-structural components. This is a non-structural component supported on another structure. If it is heavy, the threshold for heavy has changed from ASCE 716 to 22. Anyway, so that provision has changed. Changes in the determination of the horizontal seismic force F sub P on non-structural components. This is a huge change. Okay, so a non-structural component has to be designed for a horizontal force F sub P. It also has to be designed for relative displacements. If it is a piping or something, the relative displacement is what you design for. That obviously the force design doesn't go away. The relative displacement part has not changed, but the horizontal design force has changed beyond recognition. New section on penthouses and rooftop structures, new section on equipment support structures and platforms, new section on distribution system supports. Changes 1 and 2, the heavy non-structural component and the new F sub P formula are the results of ATC 120 study. Okay, I will show you. This is for a particular building, seismic design category D. I don't remember now. The seven study stall. Okay. This is the ASCE 7 F sub P force, non-structural component force level. Okay. Instead of force, we are saying the force is mass times acceleration. So we what we have on the x-axis is the acceleration, not the force. They're pretty much the same thing. Okay. So this is ASCE 716, the outer line. This is ASCE 722, the inner line, the blue. Okay, and you can see that there is a pretty significant decrease in the F sub P force for which we have to design non-structural components. I think I will leave it there. I have other stuff on the figure that are probably unnecessary to go into. It may even confuse, but I wanted to impress upon you that the formulas are different, and because of the difference in formulas, we now will be designing for lower uh, component design forces by chapter 13 of ASCE 722. There are a couple of other revisions in chapter 13 that I thought were important to bring to your attention. The first is this. The section, the scope section is revised to clarify that in addition to the components that are in or supported by a structure, the scope of chapter 13 also includes components that are outside of a structure and are permanently connected to the mechanical or electrical systems of the structure. So chapter 13 scope includes components that are outside of a structure and are permanently connected to the mechanical or electrical systems of the structure. Also components that are part of the egress system of a structure. So the scope is not confined to components that are housed within or what was the language that are in or supported by a structure. So the scope has expanded. The last item in chapter 13, I think one of the, or probably the most important part of chapter 13 are the exemptions at the beginning of chapter 13. There is a long list of things that you don't have to design using chapter 13. That list used to be in narrative form. Now they're in the form of a table, which is much more convenient. Okay. So that's what I wanted to tell you. And the only changes in substance as far as those exemptions go are underlined in the two tables that I have included in your slide set. Okay. So that's chapter 13. Chapter 14, I think that all of you basically know, is not adopted by the IBC. Okay, having said that, let me go back to this is kind of important to bring up. So chapter 14 is not adopted, but in ASCE 716, when we introduced section 12.10.3, the alternative design force level, and mandated that precast diaphragms design category C and above be designed by the alternative diaphragm design force level, we included in section 14.2.4 a precast diaphragm design force level, not force level, a precast diaphragm design procedure, and a protocol for qualification of connectors connectors used in those diaphragms. Okay. So 14.2.4 had these two important items, and we said that the diaphragms that are mandated to be designed by section 12.10.3 shall be designed by section 14.2.4. 2018 IBC chapter 19 then said, if you are designing a precast diaphragm, it has to be designed by section 14.2.4. So chapter 14 is not adopted, but in this one instance, 2018 IBC concrete chapter did adopt specifically section 14.2.4, which is obviously part of chapter 14. Now, this is available to us. This may happen in the future. I do not know. It was done. It was done because there was no other way of going forward. Okay. Now to complete the story, what was in 14.2.4 became two different ACI standards. ACI 550.5 is the design procedure. ACI 550.4 is the qualification protocol for connectors. And those have been adopted by ACI 318.19. Since 2021 IBC references ACI 31819, we deleted the adoption of 14.2.4 from 21 IBC. We also deleted section 14.2.4 from ASCE 722. So this was a temporary thing, but this is something that is available to us and may be utilized in the future. Okay, chapter 15, design requirements for non-building structures. Extremely important chapter, has important changes from ASCE 716 to 22, which I had no way of including because of time limitations. And I also wasn't sure how much of these you regulate. Then there are chapters that I would call specialty chapters. Nonlinear time history analysis has become extremely important these days. This chapter, actually all 4 chapters that are mentioned here. Seismically isolated structures, chapter 17. Structures with supplemental damping systems, chapter 18. Soil structure interaction, chapter 19. All 4 were pretty thoroughly overhauled in ASCE 716. There are changes in ASCE 722, but nothing compared to what happened in ASCE 716. Relatively minor changes. Chapter 20 is site classification procedure. Remember, we now have 9 different site classes, and the classification is based on shear wave velocity. All that stuff is in chapter 20. The site-specific ground motion procedure, remember, quite often for site class F, we have always required site-specific. Many times for D and E soil, we require site-specific. The site-specific ground motion procedures are in chapter 21. All the maps are in chapter 22. Now, we don't use the maps anymore. We go to the ASCE as a tool, but the maps are still there for some kind of obscure legal reason that I don't understand. The references used by the seismic chapters 11 through 22 are in chapter 23, listed alphabetically by the promulgating organization. Chapters 24 and 5 are kept for future expansion of the seismic provisions. There is already a candidate for chapter 24 in ASCE 728 that I will not go into, but chances are very high that chapter 24 will not be empty in ASCE 728. Okay, that brings us to chapters 26 through 31, the wind load provisions of ASCE 7. The major changes are wind speed maps for the contiguous United States have been updated. We have 4 maps, as you recall: 300-year return period map for risk category 1 structures, 700-year return period map for risk category 2 structures, 1700-year return period maps for risk category 3 structures, and 3000-year return period maps for risk category 4 structures. Those have undergone changes. The topographic factor K sub ZT, that the factor has not changed, but determination is updated. We will discuss it. Determination of velocity pressure exposure coefficient K sub Z. I call it and think of it as combined height and exposure coefficient. Extremely important. The basic wind speed, as we call it today, V, is measured at 33 feet above ground of exposure C. Okay. Now, if that doesn't get us very far. If we want basic wind speed at 60 feet above ground of exposure D, K sub Z will take us there. Okay, it's a combined height and exposure coefficient. Then simple diaphragm buildings. The term is deleted, and there were design methods that were applicable only for simple diaphragm buildings, and those design methods have been deleted. I personally very much regret that what I consider to be the best design procedure in ASCE 7 wind chapters, the simplified design for buildings up to 160 feet of height, that Larry Griffiths spent a lot of time developing. Uh, that method is gone. Anyway, so that is definitely a significant change. There are new provisions for elevated buildings. There is a new chapter 32 on tornado alerts. That doesn't affect you in California. New provisions for ground-mounted fixed tilt solar panel systems. This is huge. These are cropping up everywhere. I do not know if you regulate them, but we have new provisions in ASCE 722. External external pressure coefficients. So the last item is important in the sense that you must have paid attention. You have to in ASCE 716. The suction on the roofs of low-rise buildings, went up very considerably, so much so that there was a major attempt to have 2018 IBC not even adopt ASCE 716. So to certain people, the increases were that objectionable. Now the increases, again, these are increases in suction on the roofs of low-rise buildings. Some of these increases have been rolled back in ASCE 722, not on the flatter roofs, 0 to 7 degree roof slope, no change. The wind subcommittee has asserted that whatever was done in ASCE 716 was right and need not change. But for steeper roofs, the suction is now lower than in ASCE 716. Okay. User note added in the scope section. A building or other structure designed for wind loads determined exclusively in accordance with Chapter 26. So what this is saying is that if you just design by Chapter 26, your whatever you have designed cannot be designated as a storm shelter. If you want to designate it as a storm shelter, you have to meet ICC 500. Okay. The standard for the design and construction of storm shelters. So this is kind of important. So a building or other structure designed for wind loads determined exclusively in accordance with Chapter 26 cannot be designated as a storm shelter without meeting additional critical requirements in ICC 500. Performance-based wind design is here. We have been doing performance-based seismic design for a while. Performance-based wind design is relatively new. It is being permitted by ASCE 722. Wind design of buildings and other structures using performance-based procedures shall be permitted subject to the approval of the authority having jurisdiction. So you have to approve if somebody wants to use a performance-based procedure, and it has to be project by project approval, obviously. The performance-based wind design procedures shall, as a minimum, conform to the performance targets in Chapter 1 of ASCE 7. Now, ASCE has published a pre-standard. It's not a standard yet on performance-based wind design. Anybody that I know has done performance-based wind design has used this document. And in ACI 31825, which you probably have not seen or paid attention to, it will be adopted by the 27 IBC. In the 25 edition, we have added an Appendix W on performance-based wind design of concrete buildings. So you have designers have resources available if they want to do performance-based wind design. Elevated building, the definition is a building supported on structural elements where wind can pass beneath the building. Okay. And then low-rise building definition has not, the definition really has not changed, but it used to say enclosed, partially enclosed building. Now it also says partially open buildings. The partially open was created in ASCE 716, but then was forgotten, and this is a topic I will come back to. Definition of opening. Opening is a very big item in wind design, as you all know. So the new definition is holes that allow air to flow through the building envelope during a design wind event. Streamlined, nice, crisp. So holes that allow air to flow through the building envelope during a design wind event. That is the new definition or modified definition. Okay, updated wind maps. Wind speed maps for the contiguous United States have been updated, although this red writing is mine, although there is no discussion of these changes in the commentary. Second item doesn't interest you, but this is kind of important. Hawaii, Puerto Rico, and U.S. Virgin Islands. The maps are no longer included in ASCE 7. You have to go to the hazard tool to find the maps or the values. Then we have special wind regions all over the place, including your jurisdiction. City of Los Angeles jurisdiction has special wind regions. Up until now, the wind subcommittee has told us if you have a special wind region, you should consult somebody locally knowledgeable. So values were not given, although many California jurisdictions did provide values to the designer based on whatever studies they got done. And now the hazard tool gives you values of design wind speed, even in special wind regions, although they give you a warning that your location is in a special wind region. Okay, so that is a development. Okay, we'll ignore the break slides. So when I say that there is no discussion of the changes in the wind speed maps in the commentary, it's not only that is true. If you look at the maps side by side, you will hardly see any changes. Okay, so the Body Schwalter of ICC drew up this map. This is direct comparison. ASCE 716, the 700-year return period map, and the ASCE 722, 700-year return period map. And if you have this in your handout, if you look at it closely, you will see that along the Atlantic and the Gulf Coast, there are differences, not huge, but there are differences. Rest of the country, there are no changes whatsoever. Okay, so this is important to understand. In your part of the country, no change in the design wind speeds from ASCE 716 to 22. Yes, the maps have changed. He will probably see all over the place that the maps are changed, but they really don't have any impact on you. This is something that may interest you, the special wind region. So we picked a particular place in the east, towards the southeast. The latitude and the longitude are given. Now, if you input that kind of a location, you get all the design wind speeds. So the 300 year, 700 year, 1700 year, 3000 year. ASCE 7 also provides you with 10 year, 25, 50, and 100 year return period maps for serviceability checks if you want to do them. It also provides you with 100,000 year return period and million year return period wind speeds for whatever reason. So you will get all of that with the warning that you are in a special wind region that appears in red in the output if you go to the hazard tool. So as a jurisdiction, it is up to you to decide whether you want to use those values or otherwise, but the values are provided. The wind directionality factor case of D. Directionality factor deals with the fact that wind direction changes from one instant to the next. It is never the same for any significant length of time. So wind can be along the most critical direction of your building only instantaneously. The very next instant, the wind direction will have changed and it will no longer be along the most critical direction. So case of D accounts for this fact, and case of D is 0.85 for all buildings. Okay. There is a new item added in ASCE 722. I do not know how important it is. Case of D, you can take equal to 0.95 for round or octagonal structures with non-axisymmetric structural systems. So your structural system is not symmetric with the structure itself. Okay. I do not know how common that situation is. Anyway, that's a change. The topographic effect factor case of ZT. If you have a structure on the upper half of a hill ridge or escarpment, it will have to contend with wind speeds that are higher than if it were on level ground. Okay, so this is the change. Previously, it was permitted to neglect the topographic effect when there was an upwind topographic feature of similar size within a certain distance, similar size as the structure. However, a study has shown that little sheltering can be expected from such an upwind feature. Also, more studies are required to properly quantify such sheltering effect. Thus, in ASCE 722, topographic effect is to be considered even in the presence of upwind topographic features of similar height. Okay? So this is fairly important. Previously, it was permitted to neglect the topographic effect when there was an upwind topographic feature of similar size within a certain distance. In ASCE 722, topographic effect is to be considered even in the presence of upwind topographic features of similar height. There is a commentary to this. I think I will let you read. It doesn't add anything to what I just went over. Okay, case of Z. So even 2.5 hours will take us to 11:30. I'm at 11:15 already.
Yeah.
Okay. I don't know. How many slides do I have?
You have 120.
Okay, let me see. Okay, so the case of Z factor, it is up to 500 feet. It is listed in tables. Beyond 500 feet, you go to these formulas, or even when it is tabulated, you may want to go to the formulas if you don't want to interpolate. So the formulas have changed, as you see. The 2.01 is 2.41, and Z sub G is called the gradient height. The wind speed is 0 at the ground level. As you go up, the wind speed goes up. How quickly it goes up depends on the roughness of the terrain. Anyway, there is a height up there beyond which the wind speed does not go up appreciably anymore, and that is called the gradient height. Okay. So you see that the formulas have changed pretty materially. The Z sub G and the alpha, are given in this table, and you see that they have changed pretty significantly. These are the first changes that I've ever seen in the Z sub G formulas, ever. The old values were there for a long time. And the changes look like they're pretty significant. However, I decided to run numbers. Okay. K sub Z of ASCE 716 versus K sub Z of ASCE 722. This table is for exposure B, and you will see that the biggest difference is 1.46 versus 1.57, the last line. Okay. Exposure C, even lower difference, and exposure D, basically no difference between ASCE 716 and 22. So what looked like pretty significant changes amounts to almost no change. This is another. So the expression for velocity pressure, 00256, K sub Z that we just discussed, K sub ZT, that topographic effect factor, the directionality factor, K sub D, K sub E, the elevation factor. If you are in Denver, a mile above ground level, your air is thinner. So same wind speed, you will have the lower wind pressure. That's what K sub E accounts for. 00256 is one half of the density of the air, except that so in this formula, to be dimensionally consistent, V has to be in foot per second. But we have V mapped in miles per hour. If every time we use the formula, we have to convert from miles per hour wind to foot per second wind, it will be a major pain in the neck. So the conversion factor from miles per hour wind to foot per second wind is built into the constant. That's what 00256 is. Now the directionality factor has been taken away from that equation, has been put into the equation for the design wind pressure P, which is QG C sub P. Okay. The effect of this change is that the directionality factor now applies to the internal pressure term. Okay. So, okay. Yeah, the time is running out, so I do not know.
You have 45 minutes. 45 minutes.
I have 45 minutes?
Yeah, not till 12.
Then I'm totally fine. Okay. Okay. Now I got confused. Okay. No, we are fine for time. Yeah, 45 minutes, I'll be done. Okay, so from the beginning, when I say beginning, anyway, let's say for a long time. From the beginning of the wind design that we are doing today, we had 3 enclosure classes: enclosed, open, partially enclosed, and enclosed. Okay, And an open building is a building that has at least 80% of each face physically open. So at least 80% of each face physically open. Now that definition was unambiguous, and I have never seen anybody being confused about it. Partially enclosed meant that you have windward openings in your building, you have suction openings, but windward openings predominate so that more wind gets into the building than can get out, so that internal pressure can build up. I'll repeat. You have windward openings in your building, you have suction openings, but windward openings predominate so that more wind gets into the building than can get out, so that internal pressure can build up. Now, if a building does not fit that description, if a building is not partially enclosed, and if it does not have at least 80% of each face open, then it was called enclosed. So an enclosed building was a building that was neither open nor partially enclosed. By this definition, most buildings we designed came out to be partially enclosed. Came out to be enclosed. Most buildings we designed were enclosed buildings, according to the classification of ASCE 7, including the many parking structures we see all over the place. You know how much opening there is in a typical parking structure. They all came out to be enclosed. So ASCE 7, what ASCE 7 called enclosed, did not wasn't what somebody would expect based on the dictionary meaning of the word enclosed. One would expect a jailhouse without openings on the faces, but ASCE 7 enclosed definition told you that parking structures are enclosed structures. So there was a perception, public perception kind of an issue. So for ASCE 716, the Wind Subcommittee decided to divide what we called enclosed into enclosed and partially open. So enclosed buildings of ASCE 716 now became buildings that you would expect to call enclosed, buildings with small openings on the faces. And then buildings that we previously called enclosed but had larger than small openings on the faces were now called partially open. For design purposes, it didn't make any difference because both enclosed and partially open buildings had internal pressure coefficients of plus minus 0.18. Okay, so this was a perception thing. But the problem was that having created this partially open classification, the Wind Subcommittee then apparently forgot that they had created it. So no provision in chapters 26 through 31 used the term partially open. So there are many provisions that say this design procedure is allowed for enclosed buildings or whatever. There was nothing that applied to partially open buildings. It was just forgotten. So anyway, this slide is unnecessary to go into. Uh, so, so enclosed buildings of ASCE 722 are a building that has the total area of openings in each wall that receives positive external pressure less than or equal to 4 square feet or 1% of the area of that wall, whichever is smaller. Okay, so as I said, really physically small openings. A building that has the total area of openings in each wall that receives positive external pressure less than or equal to 4 square feet or 1% of the area of that wall. So if you have a building that used to be enclosed by ASCE 716 definition and does not meet the small opening requirement, it is now a partially open building. So the definition of a partially open building is a building that does not comply with the requirements of open, partially enclosed, or enclosed. So partially open building. Partially open structures are now referenced. So ASCE 722 now references the partially open structures are now referenced in the appropriate sections in chapters 27 through 30. Partially open structures were first introduced in ASCE 716, but no section in the standard actually referenced them, as I mentioned to you. Any provision that applies to enclosed buildings also applies to partially open buildings. That almost has to be that way because they are essentially the same for design purposes. Okay, so any provision that applies to enclosed buildings also applies to partially open buildings. Okay, windborne debris regions in which glazing in the lower 60 feet of a building's height have to be impact resistant or has to have impact resistant glazing on it, over it. Okay, so there is a little bit of change in the definition of windborne debris region. So within 1 mile of the coastal mean high water line, the word coastal is gone. So it doesn't have to be necessarily on the coast. It can be on a large body of water. Where the second addition is quite important, where an exposure D condition exists upwind of the water line. Okay, so within 1 mile of the mean high water line, where an exposure D condition exists upwind of the water line, and the rest is the same. So pretty. I would say that these are not insignificant changes to the definition of windborne debris region. Simple diaphragm building, as I said, is deleted. No longer, the term is no longer used in ASCE 722. Also, ASCE 722 does not include any provision specific to simple diaphragm buildings anymore. So gone are Chapter 27, Part 2, the enclosed simple diaphragm building. This is the design procedure I was talking about, up to 160 feet of height. I really think this is an approximate procedure, but not so approximate that it is too conservative. I really loved it when it was included first in ASCE 7, whatever edition. I still love it, and I regret that this is gone. Anyway, and the component and cladding part that is in chapter 30. So chapter 30, part 4 is gone. Also chapter 28, envelope procedure, chapter part 2, enclosed simple diaphragm low-rise buildings, and chapter 30, part 2, low-rise buildings. And our notes in red tell you that the component and cladding part probably didn't have to go because the limitation that it has to be a simple diaphragm building wasn't attached to it, but because it is kind of part of the of the main wind force resisting system, chapter 28, part 2. Chapter 30, part 2 is also gone, deleted. This comes under the Q sub I is velocity pressure for internal pressure. And in talking about Q sub I, something very important is said. So let us read this. For buildings sited in windborne debris region, it used to say glazing that is not impact resistant or protected with an impact resistant covering shall be treated as an opening. So we had that pretty much since the impact resistant glazing provision came into the standard. We essentially said that you shall either make your glazing impact resistant or you shall in design, you will do your design assuming that the glazing has been breached in the design wind event. So you will have an opening where you had glazing, and that would typically change the enclosure classification from enclosed to partially enclosed. Okay, so this is how we approached it from the beginning. Again, if your glazing in the lower 60 feet of the building's height is not impact resistant or doesn't have impact resistant covering over it, you have to design your building assuming that the glazing will have been breached in the design wind event, in which case you will have an opening where you had a glazing, and that would typically change the enclosure classification of your building from enclosed to partially enclosed. This choice is no longer available in ASCE 722. You have to make your glazing impact resistant or have to have impact resistant covering over it. Okay, you cannot get around the requirement by designing for partially enclosed classification. Now there is, I think this that what I say does not apply to design category A or something like that. I would request you to look that up. But this is in my mind, a significant change. Elevated buildings supported on structural elements where wind can pass beneath the building. You have seen that definition before. Now, this is a pretty extensive section, and some of it is fairly complicated. There was no way that I could cover it here, so I will just tell you what is in there. So the main wind force resisting system loads for rigid or flexible elevated buildings meeting both of the following geometric limitations, and I didn't reproduce them, for any particular wind direction. So the main wind force resisting system loads for rigid or flexible elevated buildings meeting both of the following geometric limitations for any principal wind directions shall be determined in accordance with this section for that principal direction. So what you have to do is given in section 27.311. What you have to do for the main wind force resisting system of elevated buildings is given right in the section. So these beach houses are very common examples of elevated buildings. Also, this is kind of important, I think. So buildings that are elevated on structural elements which allow wind to pass beneath the building. We have seen that language twice now. It was developed for typical elevated beach houses but the rest of it is what is important, as well as taller elevated buildings. A basic assumption is that the elevated building is supported by a number of distributed structural columns, and that it may include one or more relatively small partially enclosed or partially open spaces that accommodate stairs, elevators, and reception areas. So these are buildings not just elevated by on columns, but columns and relatively small shear wall cores. So this can be office buildings, residential buildings, multi-story. Okay, so elevated buildings are not just beach houses. Now we talked about the main wind force resisting system, the component and cladding on the bottom of the elevated part. Okay, so the rest of it is the same as in other building, but the bottom of the elevated part will have maybe tiles on it or some kind of covering or whatever. So design wind pressures for component and cladding elements on the bottom of flat horizontal surface of elevated buildings shall be determined using the roof pressure coefficients in figure such and such with the following modifications. So the section tells you what to do for the main wind force resisting system. It tells you what to do for the components and cladding on the bottom of the elevated portion, and the other components and cladding are mainstream. You design them the way you design for any other building. Chapter 28 is envelope procedure. The scope now has an added condition. Building does not have so a building to be eligible to be designed by chapter 28, it cannot have an arched barrel or unusually shaped roof. Now we are saying, and not sure why this was necessary, as the associated user note in ASCE 716 clearly stated that the procedure was applicable only to buildings with flat gable and hip roofs. Okay. Be that as it may, they have added this additional condition. Load cases, you remember 4 load cases, irrespective of the height of the building, your wind design has to consider the 4 load cases. And these are given in a figure in ASCE 7. Now there is a section titled load cases. This is a new section which simply includes the provisions previously included as notes on that figure. So the figure that I'm talking about had copious notes, and this new section it contains those notes. In addition, some clarifications are provided. So there is a new section, but really nothing is new. So ASCE now has a standard 72 determination of G, gust effect factor, C sub F, the force, the design force coefficient, and A sub F, the area facing wind for lighting system support poles is permitted in accordance with, so you can design lighting system support poles using ASCE standard 72. External walls of isolated circular beams, silos, and tanks. This was a very major addition in ASCE 716. Before that, we didn't have any provisions for beams, silos, and tanks, which are all over the place. Okay. So 2 changes. The notation, let's go to the figure. The diameter is D. The lowercase h as always, is mean roof height. Capital H is the eave height. No, I shouldn't say that. Capital H is the tank height, as we'll call it. Okay, so the tank height, and Z is any height above ground level, as always. So left hand side is a ground supported tank. Right hand side is a tank supported on columns. When I say tank, it is a beam, silo, whatever. So the capital H, the tank height, is now lowercase h sub c in ASCE 722. For some reason, Wind Subcommittee decided to change the notation, but then forgot to change the notation in the figure. So the figure remains unchanged. Obviously, that needs to be corrected. Second one is much more significant. The section also adds a new condition that the tank surface must be moderately smooth for the ASCE 722 provisions to apply. The tank surface must be moderately smooth. What does it mean? So this is definition of surface smoothness. Okay. Moderately smooth means d prime over d lower than 0.02. D is the diameter of the tank, as you have seen. D prime is depth of protruding elements such as ribs and spoilers. So D prime over D less than 0.02 gives you moderately smooth surface. And for the design procedures of ASCE 7 to be applicable, your tank walls have to be moderately smooth. This is a new condition added in ASCE 722. Okay, rooftop solar panels for buildings of all heights with flat roofs or gable or hip roofs with slopes less than 7 degrees. I'll read it again. Rooftop solar panels for buildings of all heights with flat roofs or gable or hip roofs with slopes less than 7 degrees. This was a major addition in ASCE 716. No change whatsoever in ASCE 722. It remains completely unchanged. Also added in ASCE 716 for the first time, rooftop solar collectors parallel to the roof surface on buildings of all heights and all roof slopes, all slopes. Okay, the previous one was 7 degrees, less than 7 degrees. So solar collectors parallel to the roof surface on buildings of all heights and roof slopes. The design wind pressures for rooftop solar collectors located on enclosed or partially enclosed buildings of all heights with panels parallel to the roof surface with a tolerance of 2 degrees. So when we say parallel, it has a tolerance of 2 degrees with a maximum height above the roof surface not exceeding 10 inches. Okay, that's what the provisions were for. Okay. Parallel within 2 degrees and the maximum height above the roof surface no more than 10 inches. Okay. Two modifications in the provisions from ASCE 716 to 22. The pressure or suction on these panels was given by this expression. Q sub H is velocity pressure at the mean roof height, as always. K sub D is the directionality factor. G times C sub P. C sub P is external pressure coefficient. G gust effect factor lumped together. But then there was a gamma sub E and a gamma sub A. Gamma sub E is array edge factor, and gamma sub A is solar panel equalization factor. Okay, this gamma sub E, the edge factor, is 1.5 for uplift loads on panels that are exposed. A panel is defined as exposed if D sub 1 to the roof edge is larger than 1/2 of the mean roof height and one of the following applies. So array H factor is 1.5 for uplift loads on panels that are exposed. A panel is defined as exposed if d sub 1 to the roof edge is larger than 1/2 of the mean roof height, and one of the following applies. D sub 1 to the adjacent array, it used to say larger than 4 feet. Now we say 2 times H sub 2. H sub 2 is the maximum height above the roof level. And D sub 2, the next adjacent panel, also used to be 4 feet. Now it is 2 times H sub 2. Okay. So that is a change. The second, the solar panel equalization factor. We had only the black curve in ASCE 716. Now we have the blue curve also in ASCE 722. Okay, the different lines are for different gaps and different heights. Okay, take a look, and if your gap is in between a 1/4 inch and 3/4 of an inch, you will interpolate between the two curves. That is the idea. So the blue curve has been added. This is the second change. Ground mounted fixed tilt solar panel systems. Okay, I this is a pretty complicated addition, and I will just give you a glimpse of what is in there. Okay. So wind load shall be calculated in accordance with section such and such for ground-mounted fixed-tilt solar photovoltaic panel systems installed in rows satisfying the following geometric limitations. Okay. So the first section that is cited gives you design wind loads. The second section gives you design support posts and foundations. Now, this is what we are talking about: ground-mounted fixed-tilt solar panel systems. So this is complicated to the point that ASCE 722 will put your panels into either zone 1 or zone 2. Okay. Now, to understand this figure, you have to, first of all, what ASCE 722 gives you is subject to limitations, and the limitations are on the left-hand side. Okay. To understand these limitations, you have to understand the notation, and the notation is given on the right-hand side. Okay, so section 29, 452 and 453 are applicable only subject to satisfaction of the limitations that you see on the left-hand side of this slide. And to understand these limitations, you have to understand the notation on the right-hand part of the slide. Now, to understand the notation on the right-hand part of the slide, you have to refer to this figure. Many times I go back and forth to figure out, what S sub t is, for instance, or what omega is. Now, once you have done all of that, have made sure that you satisfy the conditions, the figure will as I said, put your panel in zone 1 or zone 2, and depending upon whether it is zone 1 or zone 2, you will calculate very different sections from section 29452. I added another figure just so that you understand these gaps and things that they talk about in the provisions. Okay, that brings us to the last topic, which is the rollback of the major increase in suction on the roof of low-rise buildings that happened in ASCE 716. Okay, so Okay, so this is what has happened. As I said, so we are talking about gable roofs first. Uh, for gable roofs up to 7 degrees roof angle, no change from AC 716 to 22. 7 to 20 degrees, two things have happened. The division of the roof is different. AC 716 division to the left, AC 722 division to the right. Remember, 1 is interior, 2 is edge, 3 is the corner, and pressure is the highest on the corner. So the new division gives you more interior and less corners and less edges. So that decreases the suction. The division itself decreases the suction. And then AC7, the curves that give you the pressure or suction, those have changed from this to that, this to that. Okay, the overhang is now taken out. The overhangs are treated separately, not in the figure. Okay, so you have gone from left-hand picture to the right-hand picture. For 7 to 20 degrees, I don't think you will see much of a difference, but for the steeper slopes, you will see that the values are much lower as given by the curves. So the division is different. So this is 20 gable 20 to 27 degrees. You see how much of a difference is in how we divide the roof from AC 716 to the left to AC 722 to the right. And we have gone from this figure to that figure. And if you look at the numbers, this is 3.0, this was 3.6. Okay, so two ways we are getting lower values. 45, look at the division to the right, AC 722 division. It is almost all interior. So and this curve replacing that also decreases the suction on the roof. G times C sub P for roof overhangs are to be determined in accordance with section 30.7 for roof overhangs. Okay. Hip roofs. Again, the division is different. Left is AC 716, right is AC 722. For hip roofs, the division does not depend on the roof slope. This is what you get, the right-hand picture. Okay. The 0 to 7 degrees, no relief. 7 to 20 degrees, from these figures, we go to that figure. Okay. The two figures are for H over B. H is the mean roof height. L is the plan dimension parallel to wind. B is plan dimension perpendicular to wind. So we had two figures in AC 716 replaced by the one figure in AC 722. Combined with that different division of the roof, you will get relief of suction. Okay. 20 to 27 degrees, the overhang is not treated here. It is, you go to 30.7. We have gone from this figure to that figure. Okay, sorry. And you will see that there is relief. 27 to 45 degrees, this is the figure. Okay. The overhang is gone. It used to be the figures on this page which are gone. Anyway, the bottom line is that you have relief. Step roofs, the division is different. AC 716 division is to the left, AC 722 to the right. We have a new figure for arched roofs that simply wasn't there until now. The roof overhang 30.7. I will let you read it. I think time is running out, and this is something you are used to. Nothing. We have done it the way it talks about for a long time. Okay, the attached canopies on buildings. This was something new in AC 716. The canopies were in buildings up to 60 feet of height. Now the section now applies to buildings with height larger than or equal to 60 feet as well. There are two new figures that I'll show you. So this is one, pressure coefficients on separate surfaces of attached canopies on buildings with mean roof height exceeding 60 feet. So the upper surface of the canopy, the lower surface of the canopy. Okay. These are suctions at the top. This is pressure at the bottom. Okay. H sub C is the mean canopy height. H sub E is the mean roof height. Okay. So I just the fact that this is given to us, this is canopies attached to tall buildings, and we have the pressure and the suction given, and separately pressure on the upper surface and on the lower surface. The next figure gives you net pressure coefficients, considering simultaneous contribution from the upper and the lower surface. So net pressure or suction. Okay. The top is suction, the bottom is pressure, and the two different curves are for different values of H sub C, the canopy height divided by the mean roof height. So this is all new stuff that you are given. The final item is roof pavers, which are being used more and more often. The suction on the paver is Q sub H, the velocity pressure at the mean roof height level, directionality factor, and a C sub L net. The C sub L net, all important C sub L net, design net uplift pressure coefficient shall be taken as the value of external pressure coefficient G times C sub P from figure such and such, or determined by approved wind tunnel tests performed in accordance with chapter 31. Up to that is fine, but then it also says determined by methods described in the recognized literature. That I think is too loose for a standard. A recognized literature, recognized by whom? I don't know. The third item I wish were not included. But anyway, these papers are becoming more and more important. The C sub L net can be taken from the figures that are cited, or you can base them on wind tunnel testing. The important thing is that we have provisions for those papers. That even 2.5 hours, I have utilized almost all of it. But if there are questions, I will stay here for a bit. Okay. Thank you for attending on the 2 days. Hopefully it has been beneficial. I would like to thank Maria for conducting the seminars. I think there has been no technical glitches as far as I can tell. Anyway, are there any questions at all?
Yeah, thank you, Dr. Ghosh, and thank you, ICC team, for putting this together. Very informative. And again, if there are any questions, feel free to go ahead and type them in the chat.
Okay, we will then conclude. If you have questions, you may. I think it came up is last time. No, we don't see anything so far. Thank you very much. I hope they can still hear me. I don't know. Yeah. Okay.
Thank you. Thank you,
Thanks
Dr.
a lot.
Ghosh. Thank you. So we'll conclude the training here. And again, next week we have training for ASCE 41. So thank you all. And again, thank you, Dr. Ghosh, for your time. Again, very informative. Thank you all. And we can log off now. Thank you.